Yeah, so I don't know, I should thank the organizer, I guess. No, I should thank Emanuele and Roberto. It's been a joyride to organize these things with them because it's always a lot of fun, a lot of laugh, and there's nothing better than organizing things with friends or people who become friends during the act of organizing this. I know Emanuela in Sages, but I knew Roberto a bit less, and yeah, I know. So anyway, so I will move, and in the spirit, yeah. So in the spirit of the conference, I will try to not to stick to the half an hour, okay. So just to give you an idea. So I thought that maybe the people here knows me a bit for the work I do on yielding, but maybe I give you just a few idea of why I came to work on these things, and actually there is a reason why I wanted to introduce you to what is the main subject of my work, which are colloidal system. I always work on colloidal system. And the only things I wanted to retain you is that, I mean, this is the formal UPAC definition of colloidal system, in which you have basically a liquid dispersed medium and a dispersed phase. And I always looked at in my life in sort of solid particle dispersed in the medium that is a form of colloidal system. And the important things you have to retain on these things is the size, I guess, for my talk, which is 1 nanometer, 1 micrometer. That is such a size that this particle will undergo Brownian motion. So this is basically what I've done. And my whole work, my whole scientific work has been dealing with these guys using tools of statistical mechanics, liquid state theory, and mostly computer simulation. So, and I think the things I did most was actually I realized is to work generally on binary mixtures. And I did these slides only to make Thomas feel old, because when I worked a lot on binary mixture on colloids, and like ages ago, we did this interesting work in which people working in glasses, they all know about binary mixture because you have to make binary mixtures because otherwise your system crystallizes and you don't have a glass anymore. So, but then slowly during the year, I started to learn that you can do funny things. And I think with Thomas was the first time in which we learned that playing with the sizes. There is a reason why. there is a very strong, so you don't have to trust me of being the first author in any paper with Gotze, and Thomas knows very well, because Wolfgang was very strong on putting people in alphabetical order. So, you know.
Yeah, but I just didn't know.
This is perfect because I was first author and Thomas was last author.
Good enough, yes.
Exactly. So this was the work in which we looked really like how a system of a glass system could speed up if you would play with the composition and the size ratio of the particles. Something that come on later on, and we work on these glasses, binary glasses later on. And then another things I did, I looked a lot at binary mixtures of proteins and worked a lot on protein stability and phase diagram of proteins. And I realized that, you know, when you go from one component to two component, things can start to be really, really complex. And this is something I did it when I was in EPFL. And more later on, I worked a lot on binary mixture of gels. And this is also work partially I did with Emanuela, in which we looked at the idea of not doing single gels, but double gels. And I think there was also something about this. And the idea is to play with the binary mixtures. Why I'm talking about this? Because the first part of my talk will be a binary mixtures. And basically what we wanted to do in my lab was to look at yet another kind of binary mixtures, which are binary mixtures at interfaces. So these are nanoparticles that sits on a liquid substrate. And okay, that's one of the reasons why we do that, but we do this for having fun. And these sort of are spherical particles that sit in interface. And we wanted to characterize these guys for several reasons that will be clear in a moment. But basically what they do is that as soon as you are in a binary mixtures, in terms of phases you can form, I'm talking about crystals now, you enter into a zoo of crazy phases you can have. And we wanted to work on them in a situation like the following one, which is particles sitting on an interface. This is something you can do in colloids by let them sediment and go on a plane. That's really something normal. And of course, the other things is that I told you 1 micrometer below, this is where Brownian motion will work. So this guy will explore phase space. And so these are basically R sphere in the statistical mechanics sense. You can use all the arsenal of statistics. So these are characterized by large diameter, small diameter, but what matters is the size ratio and the fraction of small particle and the general surface fraction. And you can treat these things very easily as a 2D model, because that's all you need, is that you know that the small particle will sit below the big particle. And this is basically a two-dimensional disk model in which you can let the particle get closer. And at the end of the day, this parameter here, that is called the non-additivity parameter, is something that is dictated simply by the geometry of the system. So this is a two-dimensional system when particles squeeze together. And so what you want to do with these guys is to look at the possible phase you can obtain. So I'll make the story short, but basically, as I said, as soon as you have, this is something I learned during the years when I started really to want to do something useful with binary mixture, is that as soon as you jump into binary mixture, things simplify hugely. You know, it's like, as with kids, like they say, one kids, 2 kids is like having 244 hours. It's exactly a bit the same thing. And in fact, these are all the phases. I mean, disks into D, monodispersed, you have one phase, which is hexagonal, right? Whereas as soon as you have two, you can have, depending on the size ratio, all these crazy things. So this is, for example, a phase diagram we have calculated. So this is a phase diagram at infinite pressure. So at infinite pressure for right spheres, it means that for this guy here, you are calculating the best way to pack them, because this is what the criterion will tell you. And you obtain all these structures that are all tiles that you can use to regularly tile the space and have a regular structure, okay? So you can have from the craziest structure to the most simple one. Of course, you will always get hexagonal. You get a mixture of them, and these are the infinite pressure phase diagram. And what I wanted to, I mean, that's interesting, but what interests us is that this special two structure that you have here, because you see immediately that they have special properties, because if I take two of these structures, right, two of the tiles, I can put them together very easily without losing any space. And at the end of the day, I can pack all space with a random structure, which is basically a random tiling. And we are now going into quasi-periodic structures that are quasi-crystal, that possess not a translation invariant symmetry, but that present still peaks that are in the Bragg diffraction peak. And so with this, you can easily pack the space. And you see that you have, I mean, from the statistical mechanic point of view, you have a lot of this realization, right? And people looked at these guys in the 90s and showed that basically, of course, you gain a configurational entropy. And in fact, you can show that this configurational entropy, if you now forget about the particle, but you think about the tiles, is optimized for a certain size ratio, right? And so we wanted to see if in a thermal system, we could see this kind of structure and where you would expect to have square and triangles, right? And it's very slow. And so this is a random tiling, so you have Lagrange error that gives you Bragg peaks, but it's still aperiodic, and these are the famous picture of several. So this is actually a nanoparticle system that is quasi-periodic, and this is probably it's the Bragg peak of this guy here, right? So we wanted to see if you could see these things, and of course, for these things you now have, because the system to calculate the most packed structure rely on the fact that you have finite box, whereas if you want to see really the things how going on and how they evolve, you have to do a proper simulation. But at this time, you have the phase diagram, you know where you expect a certain phase, you can do simple molecular dynamic simulation. Now the pressure is finite, and you see what phase forms. And so now you vary the size ratio to the fraction of spheres. And so if the one before was a sort of a thought experiments, you cannot go to high pressure, this is much similar to a real experiment. Now you have a finite pressure, the particle can move, diffuse, and do whatever they want. And when you do this what for us would be the test whether these things are doable experimentally. And when you do this, you find a lot of regular structures. So I don't enter into detail, but all of these kind of funny structures, now you see these are a bit defected, because now these are real things. There will be defects. Some of them will have less defect or more defect, but basically where you would expect those phases, you get them. So in particular, the S1, which is a small sphere in the middle of the big spheres, and this one here, which tells us that somewhere here you should expect to find those quasi-crystal, and in fact you do find them. So if you put yourself at the recipe that was predicted to maximize the entropy, you do find a QC12, which is a 12-fold symmetry structure, exactly as I showed you before. But you also find another one, which is a QC8, which we are not expecting, that is now 8-fold symmetric. And you can explain this from a geometrical point of view very easily, because basically this is the structure you get. These are always numerical configurations that are full of defects. but you can then find your tiles. These are the tiles that are formed by the particle. And at the end of the day, in this QC8 structure that we were not expecting, you realize that these are due to the fact that you now don't have 2 tiles, but you have 3 tiles. So you have these isocell tiles and two kind of tiles of different structure. And of course, this one you can put it here, this one you can put it here, so you can tile space. But if you do this, you will obtain a quasi-crystal that now is 8-fold symmetric. And in fact, you can see that basically all the orientation are represented more or less equally, and this is a good representation that in fact this is going to form. Okay, so this is more or less what we did, and this is my introduction to say how complicated things can be in thermodynamics. And so this was the thesis of this guy here, Etienne Fayen, was discussed 2-3 years ago. And then we really wanted to think about these things experimentally. And of course, for us, it's normal to talk to colloidal people. So we are talking with Roel Dallens, that is interested in doing, is really an expert on doing colloids on interest rate. But then during COVID, we have nothing to do. And so we had a lot of money because, I mean, all of the money of the group, I'm in a theoretical group, so all the money is of travel. And so there was a lot of money at the end of the year. And so I actually bet with my colleague, Frank Smallenburg, to say, you know, what if you take these things and you put them, instead of working at micrometer, you work at the millimeter, and then you shake your things, right? There is this whole story of mapping thermodynamics of system into macroscopic systems that are shaken. At least we say this all the time, or we do shows of this to the students all the time, right? And so he betted that it was not possible. And generally, Frank is always right. That's sort of like the rule in the group is that, but this one go, okay, later. But I mean, of course, the situation is clear what the problem is, right? Here I can use all the full arsenal of statistical mechanics. Particles, they move on their own. I mean, because they're thermal agitated, if you just look at them, you know that more or less they explore well, they have elastic collision, that's important. They will reach thermodynamic equilibrium, and you will have something that you have to maximize or minimize, that it's a thermodynamic potential. If I now start to shake this kind of guide, which now are millimeter objects, of course I have dissipation during each collision, right? And if I have dissipation, I have to inject energy into the system, because otherwise particle stops, and this is what comes from shaking. But the very moment you do that, you enter in an equilibrium steady state, and basically we know very little about, at least I know very little about the statistical mechanics of this. I mean, there is, but it's much less solid in foundation and still discussed. And so there is no reason why I should expect these things to work. So yeah, so I'm not crazy to start the experiment before the simulation. So we do the proper simulation. And we were lucky enough, so I talked with a good friend of mine in Rome, Andrea Puglisi, who's an expert in granular system, especially granular gases. And he had a PhD at the time with whom we started to interact. And he can basically do molecular dynamics simulation that are really accurate. Now, I don't want to get into the details, but these are really engineer-like simulation in which you have a real vibrating plate that exchange energy, and you have rotation, translation, and a proper way of dealing with the interaction in which you have dissipation and everything. Yes?
For engineering ones also put in like rotational friction thing, all of that is here, rolling friction.
I don't have it here, it's called Mermid something. It's very complex. Gazillion of parameters.
Yeah.
Gazillion of parameters.
Yeah.
So,
rolling friction, all of that.
So there is rolling friction, the tangential friction, normal friction, tangential elastic part. This is also a model that also have a memory. So during the collision, there is a part that is a viscoelastic. So it's a mess. I mean, I don't do it. Labs does it for us. But the student knew these things very well. And so this is how they look, right? And so when you do that, you can say, okay, now I can do simulation. Let's put myself exactly where I do expect a phase from the equilibrium point of view. There's no reason whatsoever why this should work. You do that, you fiddle a bit. I'll tell you what it means fiddling a bit, but I give you first the picture, and this is somehow this video starts. This is what you see. Now you're looking the things on the top, but the things are vibrating. They're vibrating, and you see that it's like, if I showed you this is a grain boundary growing in a normal thermal system of RCS. I mean, there would be no reason to affect. But this is a non-equilibrium system. So the trick here is that, of course, now you have frequency and amplitude in your shaker that are very important, and you have to play with them because you know all that these things tend to mix like hell, right? The Brazilian nuts effect. But now I'm 2D. I'm doing computer simulation. These guys are perfectly flat, so there's no problem whatsoever. And if you follow the thing is that, you can study the Q4, which is basically a symmetry parameter that tells you that this structure is fitting. So this is completely non-equilibrium dynamics, and now it's showing you exactly what you expect for equilibrium dynamics.
Giuseppe, this one, where in your face? Oh, there. Yeah.
There,
Okay.
in the middle of this one, exactly where we do expect this phase here, which is the four spheres, the one in the middle. And then, of course, you want to go for the big prize, which is quasi-crystal. And I have a horrible video of this. I should update this. But the long story short is that this guy also, in time, in QC8, where you would expect QC8, formed this QC8 structure that you would get. So the simulation were encouraging. We bought the machine and we hired the PhD of Andrea Puglisi from Rome, and we say, you come to us and now you do experiment, you don't do simulation anymore. And he agreed on that. So he built the machine, the apparatus, which is at the end very easy. I mean, it's something that experimentalists a theoretician can do. This is the machine. There is just a barrel here, which is the vibrator, and then you have a camera. And this is a cheap camera. I think this camera costs 70 €. I mean, it's a good one. It's 60 hertz, right? Nothing fancy. And I mean, the first day my student could get tracking with no problem whatsoever. So that's the machine. And so when you do that, you put yourself there and you run your experiments. And now you follow the fraction of S1, and you see that the fraction of S1 grows, and you get exactly the crystallization you would expect, completely out of equilibrium. So there's no reason why this should happen, because thermodynamics doesn't hold here. Yes, Purple.
Sorry. So in your top phase diagram, right, the ones that you had with colloids, what temperature should I be thinking of?
And there's no temperature there.
I know.
Because these are spheres, right? There's a very
but there's Brownian motion.
Exactly. In that world, whatever I do with temperature wouldn't change it.
Can be scaled it. Scaled up.
Because the distribution of velocity will be always Maxwell Boltzmann, whatever you do. So that we don't care about this. But it's important here.
Here, yeah.
Because, so yes.
Pressure.
These are Brownian colloids.
This.
The earlier.
Yes. The line, the underlying, yes, it's an MDD event driven, so it's like Brownian colloid.
Sorry, Max pointed out I should really have asked you about the pressure, not the temperature in the previous ones.
Yes.
And what effect, I think you said something about what effect pressure has on that.
So the first phase diagram I showed you before was infinite pressure. This was a finite pressure. So this means that basically the way you do, it's a microcanonical simulation. So you fix the size ratio, you fix the fraction, and you fix the overall packing fraction. This will give you a pressure. So of course there will be a pressure at which the crystallization will occur. Below will not occur. And of course and so the pressure, so what is the question about the pressure? There's no pressure here, of course, because it's a bit more complicated.
Yeah, we can come back to it. I think if you want to think of this as an ensemble and the Edwards ensemble, then we should try to map it.
Exactly. So, but we haven't done it yet. We start to argue, because here you can define a pressure. Because, by studying the collision, you can come with an effective pressure. People in out of equilibrium do it all the time, like in these MIPS, right, phase separating things. So that's something that can be done. But I want to comment on temperature, because this is important, because I remember when we discussed this with Emmanuel Trisac, you say, okay, but this is normal, because somehow you put yourself in a situation in which somehow you are in an equilibrium system that mimic an equilibrium system. But if you look at the temperature of these two guys, they are not Maxwellian, and they don't follow equipartition. So it's, that's, which is what you learn in first year of molecular dynamic simulation at equilibrium. If this doesn't work, you screwed up your but this is expected to be like this, okay? And so then we did also the QC8. You have to look in Q space, right? Because in this way, it tells you less, because it's a much more amorphous structure, but you see exactly all the peaks. And you can, in fact, so this is at the beginning and this is at the end. This is excruciating. Yeah, and you can find the tiles that I was telling you about in your system. And in fact, you can reconstruct the tiling and look at the distribution of tiling. Somehow is exactly what you would expect from computer simulation. So these are the experiments. These are the simulation. And somehow these are the equilibrium simulation. The kind of structure, the distribution of angle you get are properly described. So you do have a lot of defects, but you get these finite peaks here. That you, I mean, even quite a bit of a series of peaks, right? And so, okay, so this is, I mean, yeah. So to give you an idea of how the experiments work, this is following the experiment. So I would like you to appreciate the time. This goes on for 10 days, and you see the particle. So it's interesting. There is something to say about the way this crystal works, because the yellow tiles are tiles that are the right size, the right shape, but not well oriented. So you get a lot of this shape, this tile immediately. Then it takes a very long time to assemble in the right direction, and this is what takes really a long time to form. So, so okay, this is the first part of my talk on binary mixtures, and basically now we have reached this sort of human scale Vibro grain in which you form all these beautiful sort of things. And I must confess that while it's intuitive to say, I mean, you can go there with intuition, like, I mean, I put myself in the same place of equilibrium, but I go out of equilibrium. We have no idea why this works yet. Okay, so then you teach me, Edward. Yeah. And I know that's because, I mean, we were looking about those, of course, we are looking for something like entropy, but then we look in Edward entropy, and this is for us for things that are not related.
People interpret in so many different ways. So we need, I think only one way to really do it.
Because this is really where we are stuck. So,
can you just flash the phase diagram for me one more time?
If I do like this, the phase diagram. Here it is.
So can I ask a question about what Luke said? I mean, so the point in your phase diagram where you're getting these quasi-crystalline ordering is one where you're not jammed, right?
Yeah, absolutely.
No, it's not jammed.
Not jammed.
Yeah.
Edwards, can I just say something? People misrepresent what Edwards said. Yeah. Edwards said two things. Yeah. Edwards said that if you look at jammed packings, then there is, he talked about volume first, and then we've been talking about stress. And when I first met him in 2009, he was talking about stress, so we didn't discover it. But then he said that the slow dynamics of granular systems is dominated by this ensemble, which everyone forgets. Not, so if your kinetic temperature dominates, then Edwards is lost. Yeah. But really, if you have a very dense system where you're basically hovering over your inherent structures, then Edwards works. Yeah. But Edwards, in the sense of thinking of the stress, or the extensive version of stress, the force moment tensor, as the analog of energy, not volume. Maybe volume comes into. So the microcanonical is a fixed stress ensemble. It's a different microcanonical. But in so many ways it works.
So we need to talk because this is definitely not in our arsenal. So
it's just amazing because everything looks like equilibrium because there is a kind of an underlying microcanonical ensemble. And it's not based on energy because energy is being dissipated, but there is some other extensive quantity which is conserved. And, so and that's sort of the basis of all that I spoke about in the conference, that there is a topologically conserved quantity.
So this is really
cannot be changed.
We got stuck in terms of understanding this. And even Andrea, who comes from Rome, but from the sort of kinetic theory kind
the kinetic theory.
So but really, I have no clue how to underpin this. I come from equilibrium statistical mechanics. I don't have a clue how to do this. We should talk.
So, just to understand better, should I understand what you're saying as, the Edwards entropy being the equivalent to the configuration entropy?
No, it's not configuration.
It's not configuration.
It's if you take shear stress or pressure. I don't want to call stress because stress is an intensive quantity. You think of the extensive version of that. You basically ask, if I look at the extensive version of pressure and change it by a little bit, how does my number of configurations change? That's the entropy. It has nothing to do with volume. It's how I can. So the point is, if you fix the stress and the thing is completely static, and this is Max's thesis, with you break the system up into sectors,
Okay.
which cannot, so if you don't change the boundary stresses, you cannot go from a configuration in one sector to another. Basically, I'm saying you have to make macroscopic changes to, and it depends on how big these sectors are. There can be sectors where there's only 2 or 3 states.
Yeah.
There can be sectors where there are exponentially large number of states. We don't know that, right? That counting we have not been able to do, right? But if you just postulate that, that there is an entropy like that, which is completely Edwards in the sense that every microscopic configuration that is allowed by your constraints, by your shaking and your external, is equally sampled, like a microcanonical, then it works. It works amazingly.
And so you have to see the response to the pressure variation. We will be like changing the packing fraction here, and you can even measure the pressure.
Right. I think if you just measure the extensive version of pressure.
So we really need to talk because now we are really looking how to do these things.
And it works, and that's precisely why we've done all of the scaling, etc., in suspensions, which look exactly like equilibrium, and that's why it works.
Even in vibration, so as long as, if I understand well, as long as the vibration is there, but it's not like a granular gas.
Correct. As long as your kinetic stress doesn't dominate the contact stress.
Yeah.
If the kinetic stress dominates your contact stress, that's the kinetic theory part of it.
And nobody has looked at this, because when I called Andrea, I called him Andrea Puglisi, I said, people must have looked at this. I mean, it's so stupid. I mean, no, nobody has looked at this. So I was pretty surprised because, I mean, in our world, we do this all the time, assembly, but nobody. Okay, thanks.
So the work with Stefano and Dan.
Yeah, that's the volumes. We wanted to test whether that works, right? That's a different... Maybe we should come back to it, because Edwards is said in so many different ways that we... so that work tested whether Edwards' original proposal that you fix the volume of a system and everything is equally weighted doesn't work except just at the hard sphere point. That's not a statement about the stress ensemble. The stress ensemble works. The volume ensemble doesn't work, equiprobability-wise. Because volume is not conserved, quote unquote, in the same way that stress is. If I overlap particles, in what sense is volume conserved? Right? I can just change it through local things. If I'm a hard sphere, yes, it's conserved. I can't do anything if I have jammed packets.
Okay. So this really is something we don't understand. So would be. Okay, maybe I move to the second part. I don't know, but it's quite a bit of things. So that's now I want to move to something slightly different but related, and of course this is something that Shri talked a lot about. He's expecting what I'm going to do now, which is this. Finally, after 13 years, I have updated the picture of Shri in my talks. This is a picture we take yesterday afternoon in front of a devil pushed down from an angel. So,
Where is the original picture?
sorry, it's with you.
Oh, I missed that.
Literally, this was our place in Lausanne. I think you were like 3 or 6 months or something like this. So I've been showing all the time this of Shri, and there was another taken, but that was lost. So I say this weekend we have to take care of this and make this change. So now this is the version. So during the years we had a lot of students and postdocs through different ways of sourcing, but most of it, I think it was Cefipra, which was very fundamental. And I'm not going to review all the things on this kind of system because Shri has done already this last week. I just give you a few important results. If you remember, what we did was to work with this oscillatory protocol, but cyclic, right? In which you had this gamma max, which is the amount of how much you deform your system, right? And then the main things I want to show you about this, because everything was discussed and showed you by Shri last week, is that it exists basically a critical strain. So this was the original work. Forget about the lines. Now we know that that was something we thought it was, but it was not. But the important things you want to keep in mind is that you have basically a critical gamma, which is the amplitude of your oscillation. And below that, the system lives in localized states, or often, as I think Stefano referred to them, plastic localized, plastic reversible state in which you go ahead and back and you rewind your configuration. And above that, you remain in a diffuse state in which the diffusivity, a sort of diffusivity, remain finite. So you have this transition from what sometimes is called an absorbing to a diffusive state. And of course, this is something that was pretty much looked a lot in the very famous paper by Pine and Cohn workers on colloids at low density, in which you have this fraction of active particle that jump from 0 to be finite in, again, oscillatory. Then was also looked a lot in this two-dimensional system by Keimen Aratia, who looked at colloids and an interface, and then you move this needle, and you see that you train your system into entering an absorbing, and this is a diffusive state, and this is an absorbing state with a critical threshold for that. And that's another one that is really on colloids, right? So this is only 3, but there are plenty of experiments and simulation. Jim also discussed with us the other day on his beautiful X-ray experiments. But what I want you to keep in mind is that in this world, which is a world of non-equilibrium statistical mechanics, these things are sometimes called absorbing phase transition. And one of the big discussion, the idea is that in this kind of system, so this is fine, is that you are injecting energy into the system because you keep doing your left and right, but below a certain threshold, everything gets absorbed. So these things are still going back and forth, but they go back in exactly where they were. Whereas in the above, you have these things that are always dynamic, right? And so what happened to be important in these kind of things and not yet really pinned down is that you can have transition that are sort of continuous transition, first order. You can have transition that are first order transition. It turns out that what we did was a first order transition at the time. For the sizes we had, exploration we could do, we couldn't realize now. We all accept that this was what I showed you before in fact is a jump of the diffusivity, is not a continuous one. And you can even build sort of effective field theoretical model that varying a certain parameter, you can have both transition. So you can pass from a continuous to a discontinuous. Why am I saying that? I'm saying that because one day, one of my students came back to me and he said he was working on these things and was running simulation at very low density. And at some stage, nothing moved anymore. I mean, things were still moving. I mean, it was pumping energy in the system, but everything stopped. And the reason is pretty simple, in fact, is that these particles now, these are real grain. And so they interact with the walls, which, I mean, you model as I say, in an engineering way, they have dissipation. And basically what happens is that if you give a speed to your particle, the particle will slowly stop and eventually go in one of these sort of rattler up and down, right? But on top of that, you also have another thing, is that while you do that, if two particles collide, there will be a lot of energy because you are pumping energy in the Z, and the collision are the way to pump in general in XY, right? So you have a sort of fight between these two effects, right? And in fact, you can see that if you send a single particle, the kinetic energy after a while dies out because the particle lose their energy and they just keep, this is the kinetic energy in the XY plane, right? The Z, there is always energy. And so when you do that, we find out that in fact, if you go at low density, so these are simulation now, your system enters slowly into an absorbing state. So here you're still shaking your system, but eventually everything dies. And at high density, everything moves. And there is clearly an indication of a sort of, I don't know if it is the but, a sort of a critical density where you can see that you have sort of avalanches. You can really appreciate at this density, this explosive nature of the collision. You see that they have a whole ballistic tract that comes from this sudden injection of energy. And when you do this, you can study diffusivity or you can study the fraction of active particle, and you see that you have this sort of continuous transition. So far, looked like the Pine transition. And then we started to play because I recognized immediately, thanks to the work we did with Shri, okay, this looks really similar to what we did. We continue to work. And then at some stage, we find out that while the student was playing with parameter, you could have, in fact, a continuous transition like this one and a discontinuous transition. So both were present. And the only thing that changed in this simulation was actually the height of the confinement. So passing from 1.15 diameter to 1.55 diameter, so this is such energy, such amplitude and frequency that particles shake, you pass from a continuous to a discontinuous transition. No idea why this was happening. And so what we did is that, okay, we go back to our usual skill of simulators, which is watch what things are doing. And so we looked at the things, and this takes few seconds, but if you maybe already now, you might start to see something going on, maybe more and more. Yeah, you now start to see that something is going on, right? So you start to see a population of particles that are synchronized. In fact, if you play all of these, all the particles on the discontinuous transition get exactly synchronized and they move at the same time in frequency with the plate. So here you see only the particle, but there is a plate that is pumping the particle, okay? And so then you can look at these things, you know, Kuramoto's oscillator, all these parameters that are typical. It's basically a phase shift. It's a parameter that is one if things are synced, it's different from one if things are not synced. And then you can look that for the, so there are particles that sync and there are particles who do not sync. And then you can, I mean, this becomes like a sort of a chaotic sort of study, a sort of dynamic system, because now you can study, let's say you fix the frequency and you vary the amplitude and the height, which are two length scale of your system. You can draw down a map of synchronization. So this is, one is synchronized and whatever is not one is asynchronized. You get these bands here, which are area of synchronization. So this is amplitude and height. So this is a property basically of your experiments, how you set up your experiment. And it turned out that indeed in the synchronous state, we have a discontinuous transition, and in the asynchronous state, we have a continuous transition. And the reason this we understand now. I mean, it's different from the other. The other
height on the height on the y-axis.
This is the, this is the height and this is the amplitude, yeah. And it's fixed frequency. You could play with the frequency, we'll give you an extra axe. If you play with the frequency like this guy get modified. I mean, you have to be strong enough that the particle bump up and down. That's the only thing, yes.
Simple setup. Kadanoff has this reviews of modern physics called Built on Sand or Built Upon Sand. His postdoc then, who I don't remember the name, did some very simple simulations to show how you set up the system or what kind of dissipation happened in the boundary. You could get synchronized motion versus asynchronized motion just with two particles, I think. It was just, the point was boundaries, conditions matter.
Things, the dissipation. So my student, Rafael, did a simple model of the molecular dynamic simulation of, I mean, sort of Lennart Jones or something, shaken. As soon as you put a bit, I mean, you have to spend a bit of time inside the wall. And then you see bifurcation, I mean, you see phase locking, bifurcation, so they go doubling, and then house. That's what you see. But it's a single particle. It's not like you know.
It's not a collective thing. No.
What is called
one particle interact, how you dissipate.
And the reason for that, why you get this is pretty simple, because now you have two time scales. You have a time scale tau d, we call it, which is the time of the next collision, and a time tau s, which is the time of the takes to synchronize. And you can estimate this, you can see that particles themselves, they have a characteristic time to synchronize. So there are two regimes. One is when the collision happened before the synchronization, and this case means that the particles are not synchronized with the plate. And so basically most of the collisions are not planar, and there is a huge injection of energy into the system. And so there is a large Z to XY energy transfer. And in the other case is when, so in this case you have a continuous transition. In the other case is if your diffuses time is, collision time is shorter than synchronized, the particle will hit each other once they're synchronized. And in this case, they will collide in plane. So that this guy will go like this and will collide exactly in plane. And when you collide in plane, you inject no energy in the XY plane. And this makes the transition very small, in fact, and this makes the transition discontinuous. And this is the mechanism. This is the mechanism.
When you change this, for example, it will make your particle a little bit soft.
I mean, this time here will depend on the mechanical properties of the particle. So what I'm hiding here is that on top of that, we developed a full coarse-grained model because we don't like to work, we don't even know what they are, like, all these mechanical things, engineering things. And we basically map everything in a two-dimensional model in which you have an injection of the energy, a coarse-grained model.
But what's controlling the synchronization time?
So the synchronization times, the property of the particle, given the property of the particle, is the setup.
Vibration, height, and so on.
Height, confinement, amplitude of the vibration, and frequency of the vibration. In a way that is, I mean, you you can take one of these parameters and you will have a doubling, the typical, logistic map kind of things.
So both of these are emergent timescales, right?
All of these are emergent timescales, but the first one you can easily get by saying, okay, working on what is the typical distance between the particles.
Exactly. Yeah, mean free path and yeah.
It's pretty plain vanilla.
But for example, if you modify the properties of the particle in a strange way, you could get them to deform when they collide, and maybe it's not true anymore than if you have a collision in the synchronized states, you don't transfer.
Sure. I guess there are plenty of things you can do, yes. The nice thing of this is that, these are simulations, but these are literally 1 millimeter things you buy almost at the supermarket. I will not enter into the detail, but you understand basically what we did. We developed a kinetic model based on this, and you can show this transition, which is, the results are here. There's another thing that is interesting, then I'm basically finished, which is, if you look at the structure of the absorbing state, they are indeed very different, so I'll give you this. So in the synchronized state, you end up in a cluster-like structure, whereas in the asynchronized state, this is all the silent matter, you end up in a sort of very uniform things that is in fact hyperuniform. And also the way that the velocity distribution, in this case you have two populations, whereas in one here you have one population.
That's hyperuniform.
Yeah, you can see that. You can even
What is hyperuniform?
the asynchronized state. So the one when you have a continuous transition. My student developed a little hydrodynamical model for this, in which we really show that you have this uniform state.
Sorry, what are the two plots?
So here is
no. The distributions. What are
the velocity? So this is the velocity, and this is like the modulus of the velocity. So you basically.
Oh, I see. Okay.
You see that in this case here you have like two populations, like here and a tail of fast particle, and you really clearly see that. We are on the process of characterizing this, but this is basically all. Just I show you final things, which is one can ask about experiments. So these are my experiments. I went there with my mobile phone when the postdoc was doing, and you see that you have the absorbing state. And now it's for me was quite funny, because it's the first time in which I really touch with my hand the difference between a simulation and an experiment. So in simulation, this is an absorbing state. But you see that it's activated by itself, because there would be, a little asperity of the things and reactivate, and this is very unstable. You have explosions, right? Whereas here, this is the high density. But Andrea did the things properly, did the tracking. So these are real experiments properly done. And when you do, you see the fraction, right? You see this transition. Getting discontinuous to discontinuous is a bit more tricky things, for the reason I was telling you. Impurity on the system will make the thing difficult. But, and this is really my last slide, we do have the synchronization. So this is, again, done with my mobile phone. It's slowing down. You see that are dancing together. And so depending on the height, so this is, you attach a accelerometer to your things, and so to your plate. So this sinusoidal here is the acceleration of the plate, and the little bumps you see are the collision of the particle. So for this height, for example, Andrea got collision no matter where, and for another height, you get synchronization. So this at least we get. We still have, probably the problem is that we need to find an indirect way of detecting the two transitions, something like some scaling exponent, because the transition itself, I don't think we are going to see. We are not going to see. It's clear that we are not. So I think I skip all of this, because it's sort of like, okay, you understand.
Basically, your relative momentum in the z direction has gone away, right?
Yeah.
Things are just vibrating with the
exactly. Yeah. So they're still active, and they do a lot of noise. So it's 300 dB when you go there. It's like it's horrible for this. But so for me was the fun of working with this, going back from equilibrium and so I should say going and go back, equilibrium and equilibrium statistical physics. And these things here, I think we were discussing with others, was completely an accident we discovered. So it's still a lot of fun, and is something we are really playing on these days. And so these are basically the people with whom we work more in my lab. So most of the work is on the grain is Rafael and Andrea. So Rafael is super brilliant PhD student, and Andrea is a super brilliant postdoc from Rome, like everybody who's from Rome. and of course we had a lot of interaction with a little bit of help from some experimentalists in our group, and a lot of interaction with Emmanuel. Isaac, and Frank is my longtime collaborator and permanent collaborator, and Etienne was the PhD student who did all the equilibrium part on the things. Huh? And yeah, so I have this picture because you should know he got the bronze medal of the CNRS 2 years ago, which is, there are 3 levels of, this is the junior, as a very brilliant guy, and which he didn't trust at all about it. So if it was for him, we would have never done half of the talk, because no way, this is not going to work. The nice things about working with Frank is that he knows really well the things, and he's really but he really doesn't put himself out of his comfort zone. So you have to push him a bit out of his comfort zone, and then things get up. And so I don't understand anything, but I'm happy to go out of my comfort zone. So it's a sort of, I told him, we work very well. We have the thing, we work very well together. That's what our thing. And so with this, I'll thank you all.